This is the first of two videos on acid-base chemistry. This first one will kind of focus on just qualitatively what an acid is, quantitatively how do we define or describe its power, its acidity. And the second video will be more on buffers. So first of all, the most important thing to remember about acids and bases is its nature. In other words, what's the gist of it? In general, not all acids do this. We'll see an example of just a different type, but most acids, the currency, what's exchanged between two compounds or two chemical entities is the proton. So I've highlighted it or boxed it in here, this proton. So it's the focus. Now we often draw it in acid-base chemistry as H3O plus because we're saying it's that proton that's in water. Most of our reactions that we're going to consider acid-base chemistry are in water. Not all of them, but most of them. So a very high percentage. So we're going to say, in general, when we say the proton, we'll often be referring to what's called the hydronium ion. Hydronium ion. So the nature of an acid is that it donates a proton. The nature of a base is that it accepts the proton. Now we can also define this reaction by a more inclusive, broader kind of net that captures reactions, Lewis acid-base chemistry. So when we say a proton is donated from the acid to the base, we're talking about a Bronsted kind of definition where we're having a proton transferred. It's all about the proton, Bronsted. But in Lewis acid-base terminology, I guess wording, we'll say no, what we're looking at is the proton accepted the lone pair. So it's kind of more about this arrow here. It's more about the lone pair. The proton accepted the lone pair and the base donated it. You say, well, do you ever have a Lewis acid-base reaction that does not involve a proton? Well, sure, it's right here. We can say the lone pair from this nitrogen is donated to the boron to make this bond right here. So that would be then a Lewis acid-base reaction where the boron is acting as the acid site, or this species would be the acid. It's accepting the lone pair, and the nitrogen here, because it's donating the lone pair, would be our base. So those are the two models you need to kind of remember as we go into acid-base chemistry, and most of what we'll talk about from here on out will just be Bronsted-Lowry point of view, where a proton is transferred. Now when we talk about pH and acid strength, we're going to talk about qualitatively how do you look at the strength of an acid qualitatively. Just looking at a compound, let's say, can you say, oh, that compound is going to be more acidic? You can. There's some ways we can do that. But we can also quantify it by pH. Now from here on out, remember that P is just a mathematical operation. It's negative log, and whatever's behind it, they've lost the brackets. But in this case, we're talking about molarity or concentration. So when you see P, just remember negative log, and that's the molarity that we're considering of H. And it's really not hydrogen. Remember, we're always referring to this as a proton because it's a hydrogen minus its electron. So we'll look at pH of different acids and bases. Structure and acidity kind of relates to three. We can see acidity by looking at the structure and saying, oh, that's the type of structure that has high acidity. And then last, we'll look at the weak acids and buffers. This will be more of our second video. So let's get to it. I'm going to leave all this aside. We'll come back to some of these pictures later on. Acids donate protons, don't forget, if we're talking Bronsted-Lowry, and bases accept protons. We're going to have to do a little bit of some, I guess, calculations sometimes, very, very few for fundamentals chemistry. But we can say there's one really important mathematical expression. It's this, the equilibrium constant. Now K, if you're just wondering, all that means is K is kind of just products over reagents. The amount of product, so we'll say this side here, over reagent. this side here. So does this reaction proceed to the right a lot? If it does, then the product would be high, and then the reagent would be low. So if you have things like 10,000 for K, or maybe 1 times 10 to the fourth, then you could say I have a very high yield reaction. But if K is very, very low, like it is here, what that means is you have very little bit of water by itself dissociating into a hydroxide and a hydronium ion, H3O+. Very little, but a little bit does. Water does react with itself. One of the water molecules acts as a base and takes that proton and adds a third one. So we can, or I guess that's the third one here. So we have 1, 2, 3. This guy has taken the proton, so he's the base in this auto ionization reaction with water. One water molecule has taken the hydrogen proton from another water molecule. This happens. Water actually has a low concentration of our, I'll just put H plus here, and our OH minus. Oops, gosh. So it has a very low concentration. It's so low, it's 10 to the minus 14th. But please hear me out. This is a constant that we often come back to in chemistry, in acid-base chemistry, because a lot of acid-base chemistry is done in water. So we can use this equation a lot because it's always true. If it's in aqueous conditions, this constant holds fast. So if H plus goes up in concentration, this must go down. One last thing, we can often take the negative log of this value, and that would give us now 14. 14 is equal to pH, because if we take the log of one side, we have to take the log of the other. So this is going to have a log value, a negative log value of 14. And these would we just say pH and plus POH. And they're always going to equal up to 14. So I just want to give you one example for muriatic acid, a very, very strong acid. The pH of muriatic acid is -3, roughly. Well, if that's -3, then this has to be 17 to make this equal 14. So, well, 17 is really high. That must mean I have a lot of hydroxide. Don't forget, when we go backwards, this would mean 10 to the minus 17th. So this is very, very low. This is very, very high. We can do that sometimes with water. We can make one of those go very, very low, but the other one must go high to keep this constant. All right, moving on from just auto ionization of water. What if we add to water a very strong acid? Well, then all this goes away, because what's setting the concentration of the acid, H3O or H plus, is not the water doing its little bit of self-dissociation, but the strong acid. And that's always going to be equal to the concentration of the conjugate base. We'll see that we have the same amount. So it's like every single one of these molecules, HCl, if added to water, when it dissociates to H plus, and it's really H3O plus Cl minus, we can say that every single one of these dissociates. For the most part, it's like every 1 in a million doesn't. But this concentration of hydronium ion is going to be equal to the concentration of the chloride, the conjugate base. If a weak acid is used, then you don't have everything going to the right. What we see, like with HF, a weak acid, is that when you put it into water, most of it remains in the, we'll set this like the beaker here, most of it remains as HF, and just a little bit goes to the product, hydronium ion plus F minus. Very less reactive acid. HF is not as reactive as HCl. We'll learn a little bit about why. This is at low concentration, so that little bit is not going to be as much as we see in strong acids. Strong acids turn litmus paper red. They're sour in taste. Because they make so many ions, they're good electrolytes. We see a particular equilibrium constant value for this acid. It's 10 to the 6. So that means we have 6 zeros, so to speak, and it's like 1 million then over 1. Because it's 1.3, we put it a little bit higher. So we can say this really dissociates to its ions greatly. Remember the term conjugate base, so we're going to use that here. If this is the acid, the anion left is always the conjugate base. It's kind of what you would use to go backwards. It's the base going backwards. And the acid, of course, would be this HBr. Bases, just to kind of look to the other side, what are bases? Bases have the opposite sort of effect on water. They're going to generate a lot of hydroxides. So you're going to see a lot of the OH minus when you have a base. So the Kb is going to be the equilibrium constant for this acting as a base. We see that it's not as strong a base as that acid was. It's 10 to the minus fifth. So it's instead, we're saying 1, 5 zeros. We're saying 1 in every 100,000 of these goes to this side. Not many go to the product side. But in general, if you have a slightly basic solution, it's going to turn the litmus paper blue. This one's good. It's slippery. It's bitter in taste. You shouldn't be tasting what you have in the lab. They're not going to be as strong an electrolyte, but because it makes some, it's going to be a weak electrolyte. Let's look at this relationship here when we have our not nitric acid, but nitrous acid, HNO2. I can't remember the name of this, but this is not the nitric acid, HNO3. That's a little bit stronger acid. So this is a little bit weaker. Let's see what it's doing. It is losing its protons. So we can say, oh, this must be the acid. And it's losing it to this amine, just like we have this nitrogen here, accepting a proton from water. This nitrogen then would be the base. I'm going to circle that. It says to circle the base. And the conjugate acid would be of always the base. The conjugate acid is always what you're left with from the base initially acting as a base. We've already talked about Lewis acid-base chemistry. We said that the one that donates the nitrogen is the base, or donates the lone pair, sorry. And the one that accepts the lone pair is the acid. There's no proton here, so this is a more broad definition of acid-base chemistry. We see this a lot in organic chemistry. We'll talk sometimes about the Lewis acid and the Lewis base. Well, we're going to go quickly through these next few slides just to kind of know what a strong acid and a weak acid is, and some common solutions. So uric acid from our urine gives us a slight acidity. If this is 1 times 10 to the minus 7th, it's kind of neutral, but it's 1 times 10 to the minus 6th, so it's not as acidic as some things. So it's got a fairly high, you might say, pH value for an acid. So urine, black coffee would have a 5 because it's 10 to the minus 5th, and you can kind of follow this 4, 3, 2, 1. This would be 0, so a pH value of 0 actually does mean you get an equal amount of product, because remember, we're looking at concentration, and we would take and say the pH of this. So to get to a 1, you have to have a value, a logarithm, you have to have power of 0. 10 raised to the 0 power equals 1. So all these pH values of these concentrations kind of go from 6 to 0, and we go from weak acid to strong acid. So all these would be weak. Your coffee, tomato juice. Your sodas kind of slip down into the 2 there sometimes, 2 and 3s, but they're still considered weak compared to your stomach acid, battery acid, things from 1 on down. You can even go on down to -3 for some of your stronger acids. Now the base is opposite. We don't want a low value of pH, we want a high value. So we see the highest value, 14, is for like our clean Drano, things like that. It's 10 to the minus 14th H's are formed, but remember that relationship, that 14 has to be equal to pH plus POH. So if this is going really, really high, then this one has to be very, very low. That means we have a lot of OH. So remember, pH goes really high, It means we have very low amount of hydrogen, but we also have a very high amount of the hydroxide. So these would be strong bases. These would be weak bases because their pH value is starting to go from -14. They're starting to come down. So we're getting a weaker amount of that hydroxide because we're getting a greater amount. This is actually increasing the H concentration as we go down. Now it's not very high still, but we can still say, hey, we are increasing this slowly, but we're also decreasing the hydroxide in our base. All right, I said we can look at structures sometimes and say, oh, this one's going to be more or less acidic. Let's do that. This will be our last slide. We can say that if a chlorine is present, not connected to the proton, but on a carbon close to where the proton is going to be taken, then we can say it has a withdrawing effect because it is electron withdrawing. Chlorines in a bond pull typically to themselves. Well, that's a good thing because remember, if we lose this proton, and that's our acidic proton, then this oxygen becomes negative, and we kind of want things in the rest of the structure that could pull electron density away from this oxygen and help stabilize it. Well, this one's just closer. This one's further away. So we would circle this guy and say, hey, that's better to have that electron withdrawing chlorine closer to the oxygen that has to lose that proton. Now, if we have 3 chlorines, that'd be awesome. This would actually be more acidic, this proton, than the protons here or here. But what we're comparing it to is this one that has 3 fluorines. Now, hear me out. When the fluorines are next to the atom losing the proton, it's great. It's a great thing because fluorines are more electronegative than chlorine. They pull greater. But it's not a good thing when it's directly connected. So if we were to look at HF down here, remember this would not be as acidic as you might expect. And it has to do with where the charge is left. Here they just take a little bit of that charge. Here it takes all the charge. And fluoride is really, really small. We want to have that charge left on a very, very large halogen. So we would say in this case, HBr is our strongest acid. Last thing, and we're done with this slide on this first video. Remember that an inorganic acid, such as like H3PO4, is always going to be more acidic than an organic acid. And that's what we're looking at here, here. Inorganic acids, HNO3, H3PO4, H2SO4, these are all without carbon. Without carbon means organic. Without carbon means inorganic. So all these are inorganic. They don't have any carbon. Once you start putting a carbon into a structure, then you're asking about its acidity. In general, it's lower. Remember that. Inorganics are more acidic, higher acidity. Organics are a little bit lower. Thanks. Bye-bye.